Hey guys, welcome to our online tutoring for ANAT 212. I'm going to be going over chapters 20, touching on chapters 20 and 21, so we have a lot of material to cover. Okay, I'm going to get started on blood vessels. We have about 60,000 miles of blood vessels in our bodies, which is amazing. And as you can see, we've got our arteries here and our veins here. Both of them are made out of 3 layers, or tunics is what we call them. The innermost layer is the tunica intima, which on here on the artery is this one right here. On the vein is this one right here. You can see that they're different sizes and diameters. They both have endothelium, which is a simple squamous, it's made out of simple squamous cells. And these line the lumen and make it very slick and friction-free. And then our middle layer is our tunica media, and it is mainly made up of smooth muscle and elastin. This tunica media, as you can see, is right here in arteries and right here in veins, and it's much thicker in arteries than it is the veins. And this is due to it allowing for vasodilation and vasoconstriction. And this vasodilation and vasoconstriction, it helps to regulate blood pressure and shunt blood to different areas of the body where it's needed. It's also made out of elastin. And the outermost layer, which is the tunica externa, which is right here on our artery and right here on our vein, is mainly made of collagen, which is a strong protein, and it provides protection, durability, and strength. Blood vessel types and functions. We have got arteries. We've got arteries on this side and veins on this side, so I'm just going to kind of walk through them. So we have elastic arteries, which are our largest. They're kind of like an elastic band. Quick note about arteries, and I went over this before with the heart. Arteries are always taking blood away from the heart. And elastic arteries, as I said, are the largest in your body. An example of that would be your aorta. And they are the most capable of stretch and recoil, kind of like an elastic band. Then we have her muscular arteries, and these are branches off of the elastic arteries. You can kind of see here where we have our larger elastic arteries, and then they branch down to our muscular arteries. And then we have our arterioles, which are much smaller. They connect to these capillary beds down here. The arterioles are the smallest, and they're not much bigger than capillaries, and they feed blood to the capillaries. Then we have several different capillaries. We have our continuous capillary right here, which, as you can see, it's pretty, there's not a whole lot of holes in it like we have with our sinusoidal and fenestrated capillaries. You mainly see the continuous capillaries throughout most of the body, but really in the blood-brain barrier, they are the most common. And then we also have a fenestrated capillary here, which you will find in the liver, and it has gaps between its cell walls, and it also has these little pores as well. And then we also have sinusoidal capillaries. They are the most leaky, and they have large gaps between the cells, as you can see. You would find these in bone marrow, which makes sense because the cells need to be able to go into those capillaries or leave those capillaries. So we have the capillary beds here, which are made out of one of these 3 capillaries. And then we go to our veins. We have a venule, which is going to be the smallest, and then a medium-sized vein, and then the larger vein. And there's not much to the veins. The veins also have valves, which we saw on this slide here, which helps with the flow of blood to keep blood from flowing backwards, is what these valves are for. Okay, we're going to go over systemic blood pressure. Blood pressure is the measurement of force applied to the artery walls. An average healthy blood pressure, which they're changing it all the time, for the systemic circuit is 130/80 or less, as measured in the brachial artery. It's going to be higher if it's closer to the heart and lower if it's further from the heart. Diastolic is the pressure on the walls of the arteries when the heart is at rest, and systolic is the pressure on the artery walls when blood is being pumped through them. During diastolic, arteries will recoil, keeps the blood moving through the arteries. Okay, MAP, which stands for mean arterial pressure, and it is used to measure the adequacy of blood getting to vital tissues and organs. And there's actually a mathematical formula that you can figure this out. There's two different ways of doing it, which I've listed here. You can take the systolic pressure plus 2 times the diastolic pressure and divide that by 3. So I have the different formulas here, and it should give you a number. I did an example here using this one. So if you have a diastolic or a systolic of 120 and a diastolic of 80, you would use this formula. So 2 times 80 is 160, which I put here. 120 plus 160 is 280, and divide that by 3, you get 93.3. So the importance with MAP is if the number is too low, then you know that there's not enough pressure so that the organs and tissues would get what they need as far as that goes. If it's too high, it can be damaging to blood vessels. So that's why we want to figure out MAP when we're dealing with blood pressure. Okay, here is a graph, and this is cool. So it shows you here on this side, we've got millimeters of mercury, so blood pressure, right? We've got our systolic up here, and we have our diastolic down here. This line right here is our MAP. That's what that is. And this right here is the pressure in between. This is our pulse pressure, what we call pulse pressure. Okay, on this line down here, we have the different vessels. So we have our aorta, elastic arteries, muscular arteries, arterioles, capillaries, venules, medium and large veins, and the vena cava. So if we look at the aorta, there's quite a bit of pressure in the aorta and the elastic arteries and the muscular arteries and the arterioles, and it gets less and less and less and less and less as we go through the veins. So there's not really a whole lot of pressure in these veins. The main idea is to kind of take away from this graph is that MAP decreases with increasing distance from the heart. The pulse pressure decreases with increasing distance from the heart as well. And blood always moves from areas of higher pressure to areas of lower pressure. That is it for blood vessels. I'm going to go into the lymphatic system. Okay, the lymphatic system consists of 2 independent parts. You have the lymphatic tissues and organs, which is represented by this right here, and it houses the macrophages and lymphocytes. And then we have the lymphatic vessels, which is represented here, and it transports fluids that have escaped from the vascular system. Also, the lymphatic system is involved in immunity and returning fluids to the cardiovascular system. Okay, lymphatic vessels. There's 4 main lymphatic vessels. We have lymphatic capillaries, which is represented here. So you can see they're intertwined with our blood vessel capillaries. We also have lymphatic collecting vessels, lymphatic trunks, and lymphatic ducts. The lymphatic capillaries are extremely porous and under low pressure. As you can see here, they have these little slits represented in this slide, but they're very porous, so a lot of large things can get right into these flap-like mini valves. The lymphatic collecting vessels are 2 or more lymphatic capillaries that connect, and then it empties into the lymphatic trunks, which is where lymph collects or comes together. And then the lymphatic ducts, there's just 1 or 2. On here you can see here, we have our right lymphatic duct, and it drains everything in the green here. And the thoracic duct drains everything else, which is in this pink color here. Here is a lymph node, and just going to kind of go over the anatomy of the lymph nodes. So we have our afferent vessels, which are the vessels. This is the lymph goes into the lymph node through this direction here, through the afferent. And our efferent vessels are right here. This is how the lymph leaves the lymph node. The cortex is this outside portion here, and it contains the B and T lymphocytes and dendritic cells. And in this area here, as you can see, we have a lot of afferent vessels coming into, but only 2 vessels leaving out of the lymph node. And what this causes is a situation where we have quite a bit of lymph coming in with less coming out, and it kind of creates this traffic jam or this pressure, and it slows down the lymph so that the immune cells can kind of fish out the things that it doesn't want, that need to be, I guess, filtered out, I guess you could say. And then we also have our medulla, which is in the middle here, and it also contains B and T lymphocytes and macrophages. And these little lines in here, I think they're kind of hard to see, but they're called stoma. And these guys are kind of cool. They, like I was just saying, are the ones that kind of help to slow the lymph down and will fish out the things that aren't wanted. So that's the structure of a lymph node. And that is all I have, guys. So we got through that really quick. And so thank you for joining, and we will see you next time.